Hey everyone, this is Conrad from Sloppy Joe Pirates, and today we're going to be talking about a Ethereum smart contract hacking challenge from HackTM CTF 2023. This was a very cool challenge. It was called Dragon Slayer. Unfortunately, the challenges were taken down, but I do have a screenshot of it. It's called Dragon Slayer. It says, prove yourself a true champion, kill the mighty dragon, and earn the right to call yourself a Dragon Slayer. We're given a netcat port and a download file, or download zip. Like I said, very cool challenge. It's kind of a little RPG. We're going to collect some gear and kill the dragon, and incorporate in there, there's gold and a bank, different items. And to actually exploit and kill the dragon, what we're going to do is a re-entrancy attack. And we're going to use that to essentially take a quick loan from the bank for millions of gold. We're going to buy special equipment, kill the dragon, and then so that we don't run into any issues, we have to return the gold back to the bank at the end of the execution. Cool. So like I said, they gave us this download file and the netcat port. When you connect to the netcat port, it just gives you the challenge details. It'll give you an RPC port, the setup contract address, and a ticket ID and a private key. Really what's important is they're going to specifically give you that private network, and they're going to set up this contract, and they're going to give you the address of where this contract is set up. Cool. And so in the setup contract, there's something called is solved. And so this is the win condition for getting the flag. And so if this returns true, we can go back to that netcat port and it will give us the flag. And so for this to be true, our knight, which is us, we're the hero, our health has to be greater than 0, and the dragon health has to be equal to 0. And so this is the entire game. We can see there's a whole bunch of different files. There's a bank, there's bank notes, there's dragons, exploit is mine, gold coin, items, there's the knight, the shop, and then solve is also mine. So a lot of code to review, but if you've played games before, it's all pretty intuitive stuff. And the very first thing you're going to do when you start one of these things, so it's going to make a constructor. It's going to call the constructor when it's created, and it's going to build a knight object and give us 2 items, item ID 1 and item ID 2. And we start the challenge ourselves by calling this claim function. When we call it, it's going to make sure that claim wasn't already called, and then it's going to transfer the ownership to the message.sender. So right now, knight is owned by the setup contract, and once we call claim, knight will be owned by us. And this is important because this is the code for the knight, the solidity file for knight. A lot of its functions have this decorator, this modifier called only owner. And so only the owner, which is either us or another contract, if we call it from a contract, will be able to execute these functions. And so on the knight, there's a bunch of different things to do. So we can equip items, we can unequip items. There's some private methods, so we can't directly call these. More private methods, we can't directly call these. We can buy an item. If we had gold, we can sell an item to get some gold. And then there's a bunch of stuff with related to banks. So we can deposit money, withdraw money, bank merges. We'll talk about all that stuff later. And then here's how we start winning. We can fight the dragon. So the dragon will attack us. So it's going to call the dragon to do an attack. We're going to receive damage from the dragon. And if we're still alive after that, we get to attack the dragon. And this is how it calculates damage and stuff. Not too exciting. And then there's these 2 functions related to on ERC 721 and on ERC 1155, which we'll also talk about, and they'll be crucial for the re-entrancy attack. Cool. So we want to kill the dragon. We can see here we have 10 health. And at the startup contract, they gave us 2 items, item 1 and item 2. So we can see how much or what type of equipment we start out with. And we start out with here's is the item shop. And so what this is going to do is it's going to create a bunch of items. Like I said, if you played RPGs before, this should all sound very familiar. Each of these items has a name, a price, a set amount of attack power, defense power, and this anti-fire thing, which isn't too important. Basically, the dragon can do fire attacks, and if you have anti-fire, then you don't take damage from fire. And so the thing gave us 2 items, item 1 and item 2. And so we're given a bronze dagger and a wooden shield. And so it has like 1 defense and 1 attack, not that much. But if we scroll a little bit further down, there's these very cool items called the Abyssal Whip and the Dragonfire Shield. And so this does 1 million damage, and it has 1 million defense. And this is that fire protection thing I was talking about. We'll be immune to fire defense if we had this. And so obviously these items sound amazing. The only problem is they cost 1 million ether. And technically that's actually 1 million gold, which we'll talk about in a second. So if we go back to this knight class, when the night is constructed, it's going to set up a bunch of stuff related to the game. So it's going to set up this bank. It's going to set up this coin, which is what the bank uses. It's going to set up the shop, which is also going to talk to the bank. And it's going to create the dragon that we have to kill. What's interesting, when we move to the bank, within the bank itself, we're able to deposit and withdraw bank using gold coins, and the bank will give us bank notes. Again, this is all, it's very complex, not very complex, but there's a lot of moving parts, and you'll eventually find out this whole banking structure was created so that we can do the re-entrancy attack, if it seems complex. It's a little bit extra, like it wouldn't, I think in the normal game, like we would have been fine with just gold, but because there's this bank, and it's going to be specifically using these bank notes, this is where the actual vulnerability lives. Anyways, but looking just at the challenge, assuming we don't know what a re-entrancy attack is and what we're about to do, we can see that we are given 10 gold or 10 ether initially. And so if we wanted the special items, they each cost 1,000,000 gold, but we only have the initial amount of 10. Cool. I don't think I'm going to cover the rest, but there are two other exciting things. First off, there's a bunch of different types of tokens in this challenge. So the banknotes are, when you deposit gold to the bank will give you something called a banknote, and it has a certain amount of value. What's fun about the banknote is it implements this thing called ERC 721. And so Open Zeppelin, again, I'm not the expert on this stuff by any means. I think this is like some open standard that most people conform to, and ERC 721 is one implementation of a type of asset that you can create. And specifically, this is one where the assets are of different types. So if we look at Goldcoin is ERC20. I think this is like the simplest of the different token types you can create. And this is just like, this is just gold. There's only one type of thing and you have a certain amount of it. Whereas a banknote is an ERC 721. This is where there's different types of things, but everyone would only have one of those different types of things. So we're going to create different banknotes, and the banknotes will have different values. It's kind of like the title to a house, I think, is the analogy they use. So like you might have the title to the house. All the house titles are different, and there should only be one of those. The last type of coin that this challenge uses is the ERC 1155, and this belongs to the item. So again, this is kind of a combination of the other two. So in the banknotes, you have different banknotes, and there's only one of them. And then you have gold, there's only one of them, but you have a lot of gold. And here, there's different items, and you can have a quantity of items. So there's a lot of really good documentation on this stuff on the Open Zeppelin website where they talk about all this stuff. But that's pretty much all you really need to know for the challenge. And then the last thing related to, actually, I don't want to jump there yet. So cool. So that's pretty much the entire challenge. We probably spent, I did this with a teammate, we probably spent, I don't know, 3 hours kind of looking through the code. At first, we just weren't thinking about doing a re-entrancy attack. Again, we're not experts in this stuff. I've done a re-entrancy attack once in a different challenge. It was a long time ago, and that one was very obvious it was a re-entrancy attack. Normally when I look for those, I look for like a .call or something. And so I didn't realize the coins will actually make calls for us, but I'm kind of jumping ahead. The thing that was interesting and really like just smelled funky was this bank code. Like I said, there's a lot of code here, and it's not really related to the challenge. Like, why would you as a player want to deposit stuff and get banknotes? Like, the banknotes aren't really useful for anything. And so we knew the bug must be somewhere in here, and there's a whole bunch of code. There's like this merge code. And so like I said, the bank is going to have these different banknotes where you'll deposit like 10 gold and they'll give you a banknote that says you have 10 gold, but you can then split that banknote. So instead of having a banknote with 10 gold, you could have 2 banknotes with 5 gold each, for example. And then you could transfer from one banknote to another, or maybe you want to do a partial transfer where you want to like split the transfers up in between. But there's also a bunch of bugs in this code. Like if we look at transfer partial batch, there's this total value, which should be summing up as you're doing that partial transfer, but it's never actually summed up anywhere. And the only other place it's used at the very end, and so you get 0. So we assumed there was going to be a bug in here or something, like maybe you could merge or split. It's also using this weird counter structure where you do like IDs.increment. And so we were hoping maybe we could like misalign them. It's also interesting that the underlying currency thing, the banknotes don't actually have value within themselves. What actually determines how much gold is in a banknote is this mapping. So you get a banknote, but the banknote value actually exists within the bank. Maybe this is common, it seemed a little bit strange to me. Like I said, we spent a couple hours here. We didn't really know what we were doing. Eventually, my teammate started looking more into re-entrancy attacks, and he was right on the mark. Like, this was definitely a re-entrancy attack. And the trick is that we eventually found, and it was kind of right in our face all the time, was at the very bottom of night were these two functions, the on ERC 721 received and on ERC 1155 received. And this is what was important. So on this type of token, on both of these tokens, if a contract is going to receive a token, it has to confirm that it accepts that token. And I think the idea is that maybe in like ERC20, so like the gold standard, it's possible that you could imagine a situation where a contract accidentally accepts some gold, and the contract, once a contract's live within the Solidity network, you can't modify it. There are modifiable contracts, but by default, the average contract probably is not modifiable. And so, or I guess just say there are upgradable contracts. Again, not an expert in that stuff, but if a contract accidentally accepts gold and it doesn't have any mechanism for doing stuff with that gold, then that gold is effectively lost. And so I imagine that's probably happened in the past. And so at some point in I guess the newer standards for other types, they specifically do that check now, where your contract, if it's going to accept a specific token type, needs to implement this function, and it has to return this. But this is interesting. So what this means is when you accept, and this is called when you accept a banknote. So what this means is if you are a contract and you do something that eventually allows you to accept a banknote, the bank is going to be calling your function, this function, in the middle of its execution. And that's where the fun re-entrancy stuff happens. If you've never heard of re-entrancy attacks, again, not an expert in this stuff. I just know enough to solve CTF challenges. But I believe it's happened on a bunch of the big like crypto coins, and millions of dollars have been stolen. I think it's a pretty prevalent attack, and it's pretty bad. But like I said, I only solve CTF challenges. So we're going to exploit that behavior. Again, recapping, the idea is we're going to create a new contract. That contract is going to interact with the the bank. And at some point, it's going to try to give our contract a banknote. And when the bank does that, when it tries to, specifically to give means to mint, when it calls mint, the bank code is going to call our contract, specifically that function, this on ERC 721, and we're going to then have execution, and we're going to do a bunch of sneaky stuff, and then eventually we'll return back to the bank. So the specific function within the bank code that we're going to execute is split. And the reason this one is the one we're going to do is there's a bunch of requires. Again, if you're very interested in stuff, I'd highly recommend just going through line by line in the code. There's a lot of code here, and it's all very fun stuff, but I'm kind of skipping ahead. But we're going to be looking at the split function, and there's a couple reasons that you could, from just this quick scan, you could say that this one is interesting. The first off is we want a condition where it'll call mint before doing any burning. So mint is how you grant these different tokens, and burning is obviously how you delete them. We also need a function where we will still pass all the required checks. And split just happens to hit the bill on both of these as long as we're being clever. And specifically, we're going to, I think there is an official term, maybe the official term is flash loan, but essentially we're going to abuse this function such that we're going to like temporarily grant ourselves millions of gold, and then we just have to make sure that we give the gold back before this function ends. So if we take a look at the split function, it's going to accept a banknote from. Like I said, this bank has a mapping of banknote IDs to the addresses. And so the banknote IDs to the amount of gold in them. So by default, the very first banknote is 10. And so if you were to deposit 10 gold into it, banknote 1 has 10, and then you're the owner of that underlying banknote object. So we're going to say banknote from, so we could say this is from 1. And then we're going to split that into, let's say, 5 and 5. And so if we were to pass in an array 2 5s, what will happen is the bank is then going to create, this will just be the output. It'll take everything from 1 and it'll split it into, it'll create a new banknote with an amount of 5 and a new banknote with another amount of 5. Cool, and so how can we abuse this? So instead, what if we were to create let's say we had a banknote with a 0 in it. It doesn't have to be 0, but in our case, it actually will be 0. And we create the amounts 1 million. Actually, let's do 2 million. which is what we actually do in the exploit, and 0. Actually, let me get rid of these. I think in Solidity you can do that. We're going to request to split banknote 2 between 2 million and 0. This doesn't make any sense. Like, there's not 2 million in banknote 2, but as long as we're very fast and clever, we should be able to do this. So what's going to happen is it's going to go through, it's going to make sure that we are the owner of the first banknote, and we are the first owner of the first banknote. It just happens to have 0 content in it. For all of these values, we're going to go through, we're going to take the initial value, which in this case will be 2 million. We're going to create a new banknote, and here's the fun part. We're going to mint it, give it to the sender, and when this banknote is called, our code in our contract is going to execute. The first one's a little bit weird though. So the banknote was minted, and so right here we can start executing whatever we want within our contract, but this banknote doesn't actually have any value because the value is assigned here. This is where we can go back to the bank with our banknote and try to do stuff, but its value is currently 0. There isn't anything there. We just have a banknote that has 0 value. But that's okay. We'll actually, on the very first time our code is called, we're just going to say, sure, sounds good, I accept the token. It's going to loop, so now it's going to update the bank value. So in this case, this is our bank values. This is now going to be 2 million. And total value will also be 2 million. I guess we can just set that up here. Total value will also be 2 million. And it'll start the next loop. So in the next loop, value is going to be 0. It's going to update the IDs, create a new banknote. Now it's going to call mint again, and it's going to generate us a new banknote, which will eventually be set to 0. But we're still holding on to that first banknote, and now the first banknote has a value of $2 million, or 2 million either. So now in the second execution of mint, again, mint is going to call onto that on ERC reserved function, on ERC 721 received, and so we're allowed to do whatever we want in there. And now we have a banknote that has $2 million in it, and we can do whatever we want. We have execution. And we're still in the middle of some other execution thing, but that's totally cool. We're allowed to execute. So at this point, we can do a whole bunch of sneaky stuff, and the sneaky stuff we're going to do is we're going to buy those 2 special items. We have $2 million in the bank. We're going to buy the 2 special items. We're going to equip them and equipped. We're going to fight and kill the dragon. And then, this is the tricky part. We have to meet the criteria at the very end of this function. So deposit the money back. So at the very end, it's going to create that banknote, and then we're going to return. And so like I said, the current value is 0, so it's going to create that banknote with a value of 0 and total value, blah, blah, blah. So the new state of a Solidity contract isn't saved unless everything finishes completely. So if we fail this require statement, everything will revert, and even though if we killed the dragon, all of that stuff is reverted and it's like nothing actually happened. So we have to pass this check. And that's why I said earlier, we're kind of like taking a very quick loan. And so what's going to happen is total value is equal, it's going to require that the total value, 2 million, is equal to the banknote values from. And so that is index 2, and if we look here, its current value is 0. So this will fail. But like I said, if we're very sneaky, we can actually just take all that money. After we fight and kill the dragon, what we're going to do is sell the items, get back the $2 million, and then we're going to create a new banknote, deposit. We're going to call bank.deposit with all of that new money, with the 2 million. And then we're going to transfer, we're going to do a bank.transfer from our new banknote, which I think will be 5 or 4, I forget, and we're going to put that into ID 2. So at the very end of our execution, banknote, we're going to take all this money, instead of buying and selling all that stuff, we're going to put it back into banknote 2. And so these will all be 0, but we don't really care. And so this check will pass. So total value is going to be 2 million, and we're just going to transfer that money right back into the very first account. And so bank value is going to be 2 million, and then it's going to burn that, so it's going to delete the 2 million, but we already killed the dragon, we already did everything we want, so we don't care. And it's going to, it's going to burn the actual token, and then it's going to set its value to 0. So absolutely crazy stuff. We're essentially just borrowing a bunch of money from the bank, doing a bunch of stuff and giving the money straight back. And the bank has no idea that any of that stuff happened. We just created $2 million out of thin air. Super cool stuff. So that was a lot of talking. To actually debug and implement this stuff, there's a really cool IDE called Remix. And this is what was used to actually build and play. So you can load all the code in here. And what's really cool is, so you hit compile. This will take a second. But once it's done, we're actually able to deploy and debug these contracts. So This is a setup script. So normally the challenge will deploy one of these for us, and it's working in like this fake VM. Like this isn't actually on any chain, but we're able to deploy a setup script. And so let me slow down a little bit. So we loaded all the files here, and then we called compile on them. And this is where all the different panes are. This is the code. And then in here, we're able to actually deploy the code. And so what I did is I said within this like fake virtual machine, here's a fake account, has a whole bunch of gold, some gas, some value. I said create a setup script and deploy it. And down here, it'll create a setup script. So in our fake little network, we have a setup script. And if we call everything in Ethereum as a function, so there's this night thing, it by default has a getter function. And so we can call that get function, and here's the address of a night that was created. So super cool. And we can call this isSolved function. It should say false. It was not solved. Bummer. And we can claim, and we can check if it has been claimed. So right now it should say false. It hasn't been claimed. And so we can call this claim function. And so, like I said, super useful for testing and debugging. I love Remix for all that stuff. It's really hard to actually, I have a lot of trouble with MetaMask in Remix though. So to actually solve this challenge, I use something else. But this is where I developed and implemented the exploit, and then I actually launched it within Python, which I'll look at in a second. So this was the solve script that we wrote. I'm going to go pretty quickly. I think at this point, it should be hopefully clear what the actual exploit was. And I pretty much talked all the way through. This is just actually implementing it. So I don't think there's too much more to learn, but there were a couple little things like, so this is, like I said, this is the setup. This is a contract that is going to implement that on ERC 721 received call, so that when this contract calls that bank code, we can start doing that re-entrancy attack, and the bank will call our function. And like I said, when call count is 2, we can do that whole thing where we buy the items and fight the dragon. So it's actually, we're launching another contract that's going to solve the challenge for us. Cool. So there's a constructor. Like I said, we're going to pass it the address of the setup script. So the actual CTF challenge is going to pass us that address. But we're going to set it up. We're going to claim ownership of the night. Then we're just going to set some variables for future use. There's one thing interesting where we need to create a banknote ourselves that we own so that we can start the attack. And to do that, the bank merge function actually works super well. So if we go back to bank, we call merge with 0, so that this exploit script doesn't have any banknotes and it doesn't have any gold. And there's not an easy way for the night to transfer gold or banknote to the exploit script unless it owns one, owns some already, which it doesn't. But if you call merge with an empty array, so banknote IDs is just an empty array, this for loop isn't going to happen, and total value is still going to be 0, but it's still going to create a new banknote, and that banknote is just going to have a value of 0. So another nice little trick that we can use to create empty banknotes, but now we have a banknote token that we can use to call that split function. Because the very start of the split function that we use for actually doing the exploit, it requires that we own a banknote already. So one little trick, we also create a banknote, another banknote, not too exciting. When we call, so everything is kind of set up, but the script hasn't actually executed. We actually exploit it within the start function. And so in the start function is where we call, like I said, that split function. So we're calling bank.split. This is the ID to start. Everything's just made a constant, so it's easier to remember what is what. And a initial loaned money amount. So we're going to ask for a loan of 2 million. There's some weird stuff, conversion between like Ethereum and is it Way or We and all that stuff. So you're not actually asking for 2 million, you're asking for 2 million times this large value. You find that out from just like printing and playing stuff that you need to multiply it by a big number. Yeah, and then from there, this function is going to be called twice. The very first time it's going to be called, we're granting ourselves a token that has a value of 2 million, but it isn't set yet. So we have to wait for the second iteration where it grants us a token of value 0, but now we're allowed to play with the original token with a value of 2 million. Like I said, we're going to do a little transfer. We do this from the exploit script, which owns the token with the large amount of money, and we're going to give all that money to the knight because it's a separate contract, and we want the knight to have the money. And now the knight is able to withdraw the money from the bank, and so now the knight has 2 million gold. Then the knight's able to buy that first expensive item, then it's able to buy the second expensive item. We have to fight the dragon twice. I didn't cover this code, but basically it does like 500,000 damage each time, so you just do it twice and then the dragon will die. And then to fulfill our ends of the contract, we need to sell both items. So we're going to sell it for 500,000, for 1 million gold, and then we'll sell it for another 1 million gold. And then we need to make the knight needs to deposit that money back into the bank, and then it can transfer its banknote to the exploit scripts bank note. And then at the very end, we can say, oh yes, thank you, bank. I accept this token, even though we did all the sneaky stuff in between. It's too bad we can't actually run it on the official challenge because it's down, but we can try. Oh, I need to recompile. I probably touched something. But we can try running it here, and we'll just imagine that this script actually is the challenge script. So to make it easy for testing, I'm actually going to remove this and just have our exploit script create its own setup object. Like I said, this is not actually how it works. Normally we'd pass in a setup object, but this just makes things a little bit simpler because we actually exploit the challenge using Python. But once this is done, so it compiled successfully, we can we can launch our own exploit script. So we'll do launch exploit. So now we have a exploit object down here that's deployed on some fake virtual machine Ethereum thing. And it should have all of its objects defined. So we have a bank, we have a knight, we have an owner, which is actually us, and we have a setup script. So we can take the setup thing and we can grab a handle to it. So we're going to say that this is a setup. So there's a setup at this address. And so we can see the setup, it should have a knight. Is solved should be false. We don't want to claim it. No, it was already claimed, so actually we could. So we're going to see if it is claimed or claimed. Let's look at setup. Setup. We want to see claimed is the Boolean. So we go back here, claimed, and it has already been claimed. Cool. So in the exploit, to actually launch it, let's go back to the exploit script. All we have to do is press start. So we click start. Bam, bam, bam. A bunch of stuff happened. There's some, I just found out the other day, you can do console.logging. To do console.logging within a Solidity script, you do hardhat/console.sol, and then you can do, where did I put them? Console.log. Absolutely amazing. It makes debugging these things so much easier. But anyways, the exploit should have run. We can see it has gold. At the end, they have a whole bunch of gold. I bought crap. I should have made this a little bit better. But then we fight the dragon, we sell the items, and if everything worked out end, we get a green check mark, which means it seems like it worked correctly. And we should be able to go back to the setup script and see if it is solved. And is solved is now true. So we were able to kill the dragon. So very cool. So I have issues getting MetaMask to connect to a private RPC and actually launching contracts within Remix. In theory, I think it should be possible, and I'm probably just doing something wrong. If anyone knows how to get that working, please leave a comment or message me on Discord. I'd love to see how you actually do it. I'm able to set up the RPC within MetaMask, and I'm able to query stuff. I just can't launch new contracts. And I import the private key. It shows that I have enough Ethereum. So I'm not sure what I'm doing wrong. But anyways, this is thankfully I have a solve script. I've used this in a bunch of different challenges, like the Xmas CTF back in December a couple months ago. And it's all pretty standard Web3 stuff. We're just going to connect. This is the stuff you get from that Netcat port as part of the challenge. Then we're going to connect to some Web3 provider. I like to print everything out just to make sure stuff's working. So I print out the account balances. I go through all the accounts we own. Within Ethereum, you can dump the storage of a contract. So I look at the setup contract and I just dump its values to just kind of see what's going on. From here, we compile some Solidity stuff. So we're going to compile the setup code and the exploit code that we just saw within the Remix IDE. We're going to grab those out. And then we're going to deploy a exploit contract. So here we're creating one. Here's the binary interface. Here's the ABI. Or sorry, this is the bytecode, and this is the ABI. Then we call the constructor, so we can see exploit constructor. We pass it the setup contract. Then we have to wait for some like receipt or something like that. And eventually, once it's done, it'll give us the contract address of the thing we just created. So from there, we can create a new exploit object that has that address. So this is like a deployed contract, again with the same ABI. And then from there, we can call start on our exploit script. And this is what actually kicks everything out. And then we just wait for it to be done. And when we're done, the receipt will have a status field. And if the status field is a 1, I think that means everything worked out correctly. Or maybe actually if status equal to 0, I think everything worked out correctly. And yeah, with that, we're done. Basically, then you go back to Netcat. You go back to Netcat and you say get flag. You give it that ticket it gave you, and there's the flag. So all in all, super fun challenge. I had so much fun working on this, even though it took us like who knows how many hours. Most of the CTF was spent on this challenge, but it was a blast. I love playing games, and yeah, thanks HackTM for hosting the CTF. Cheers.